fantastic. Thank you very much for giving me the chance to talk here. Is really first time I'm talking to such a nice combined people, so it's very good. So as Nick says something about himself, I'm going to say something about me. I'm the quantum person. My husband is to do with blockchain, and my son a few years ago wanted to do quantum punk, but Nick and Alex stole the idea, so now we need to do it right now. But I'm really excited actually figuring out how we can bring these two worlds together, because we have not yet figured out at home. So I want to give you really from it's going to be academic talk, okay? But I do my best to make things a bit more accessible. And I want to give you a little bit of a philosophy of how I also believe, exactly as Nick was saying, at quantum computing, quantum communication, and cybersecurity, or everything comes together, okay? And maybe it's a bit of the different starting point, but hopefully at the end, we end up exactly at the same place you started. So I'm going to talk about quantum data machine. This is the thing that we know about this century. Yeah, everything is about big data. We want to collect more data, correlate more data, trade more data, secure more data. And what are we doing these days? Well, we are trying to put on top of this large language model, and then we put on top of this blockchain in order to expand this massive madness. And what will happen is massive, secure, accurate data machine will consume the energy of the planet. So while you want to make money, I want to do something good for the planet, So making sure that this cannot continue. I mean, we know it, People in the AI know it, people in the blockchain know it, and even in quantum we know it. So it's a little bit of what we need to break that barrier. And of course, we in the LIP6, we break those barriers exactly when we give up on this boring bits of 0 and 1 that can be copied and can be measured, and they are very local, and we know how to break the barrier. Okay, this is just my one quantum bit introduction slide. Qubit can be simultaneously 0, 1. You have heard about that. Measurement can change the qubit. This is amazing. We're going to exploit this for everything we want to do. They cannot be copied. Unclonability that you heard is exactly all the thing. They are not local. They are quantum correlation. All these things that for 100 years, by the way, this is the year of quantum International Year of Quantum Science. For 100 years, this sort of bug that exists in quantum mechanics is exactly fantastic tools that we use in order to make new feature. And this is more or less is the main thing that is keep coming back in order to using it. So in breaking barrier, just one slide, already Nick flashed at you so many different applications, but we can already mention it, and I guess during the talk things are carrying on. Some people talk about quantum internet. Exactly the focus of my talk will be also about this, how we connect quantum devices, classical devices using quantum communication, and all sorts of application that comes in here, sharing quantum randomness all the way to quantum cloud computing that I'll talk about. But there's lots of other application as well that if you talk about QKD, you can use those things to do much more things. It's not QKD for the sake of QKD. Maybe it's not necessary the target for blockchain, but I think it's actually, when you go through this thing regarding sharing the standard, it could be something to do with the signature scheme. We need to think about that. Or, by the way, quantum communication is the only solution for scalability of quantum computing. So quantum computing cannot live without quantum communication. The way that we're going to build any of those massive boxes to go together to build fault tolerance is through the quantum communication for distributed computing, for new functionality with big quantum devices, and et cetera, et cetera. And of course, this is what the phrase that Damien is using, Internet of Quantum Things. And indeed, Internet of Quantum Things is creating things that we didn't have before, whether it's the sensing, whether it's the automated vehicle, efficient communication, and et cetera. We just need to go to that space. So it's not just the blockchain, but it's actually quantum is coming everywhere. Okay, so as I said, what my talk is trying to emphasize is that this future, secure, verifiable, fast network quantum data machine for public good is emerging, okay? And obviously we need the help of the industry and investors and all the people to embrace this, because everybody's so excited about quantum computing, but even for quantum computing, in order to achieve all those things that they're talking about, quantum chemistry, health application, etc., you need to address the issue of privacy, you need to address the issue of the integrity, you need to address the issue of energy, and the solution of all of them is quantum communication. That was my elevator pitch, okay? So wanting to also emphasize how I see this classical approach and quantum approach are different, so hopefully again we come to the same language. Of course, classical network exists, you know, and then now this is all the full stack classical network, and the way that when you want to talk about accuracy, privacy, integrity, synchronicity, whatever application it is, in the classical world is a sort of a post-hoc application, it's a software application. We never were involved in the design of the ARPANET or internet. It's there, it's evolving, it's going around, and none of us, or at least none of me, and of people here, is just know what's happening there, and we just keep creating fantastic protocol on top. We do FHE, SMPC, Neurosolid Proof, blockchain, all of these things. All of you are doing this without knowing a single bit about what is the hardware layer there. Because it's cheap, because it's growing, because it's going all the way up. So you can keep coming up with the fancier and crazier and build the nuclear power plant to enable implementation of that. But in quantum, first of all, we don't have that luxurious to do so, but also we don't need to. And I think if you get one message from my talk, and if it's this, I'll be very happy. Because in quantum, we can have hardware, software solution together. We don't need to put everything on top and build, okay, let them build the quantum computer and or quantum network, quantum internet, and later on, I come and put an application on top. No, no, no. They are doing something magical that for whatever network they build this quantum link. I call it quantum link. People call it QKD, but it's quantum link, quantum communication link between nodes. And that enabled us to use that layer plus the top layer to make things practical. It is exactly the way that we need to do. Of course, I could do QFHE sitting on top, QSMPC on top of that, and following that, and many of the work is doing. Alex was also referring this. These are the things, if we're thinking from that mentality that, okay, I'm just taking a crypto classical machinery and I make a quantum version of it, ignoring the hardware architecture, yes, wait for quantum universal quantum computer emerge. But if you open your eyes and walk to the lab that Eleni run in here and realize exactly how they are building this building block, you use that and you put these things together and you build things that is practical. And this is a very interesting moment because quantum computing, quantum nodes are now trying to solve that problem of connectivity. So they are building new hardware, which is exactly that connectivity. And now we can go and talk to them, how to use that, give us access to that layer. You all agree with that, perfect. So now I'm going to give you a bit of the challenges. Of course, there is challenges in quantum network, like challenges that exist in quantum computing. There are challenges in every field. And these challenges, I'm not going to go at length because we are all CS people, but of course, there is challenges whether these nodes are trusted or not trusted. Can I do device independent of Roger, or I want to do some sort of living with a trusted network? It is a big challenge, but there is also progress in solution. It is also the case of short versus distant. Am I really trying to put this quantum network module next to each other because I only care about the scalability, or do I want to go it metropolitan or want to put it in satellite? Yes, that gives you plenty of different infrastructures emerging. And if you look at it, this full software stack, well, yeah, if you want to do really network compiler, software developer operating system that I just emerged from our colleague from Delft, well, there is a decoherence. These qubits are very, very fragile, so there is delay. So yes, there is lots of challenges, and we can talk about every one of them in details to see that where we're progressing. But I don't want anybody ever say, oh, there is another challenges and there is no use cases for quantum network. That drives me nuts, and let it be on the record. There is plenty of use cases for quantum network, and I will put it a bet that if somebody put a quantum algorithm in front of me and we start doing a game of I prove to you a provable quantum advantage versus provable quantum advantage of algorithm, we win. we win. It's just we are not talking about it. So if you look at the protocol zoo or quantum internet use cases, there are plenty of these use cases. They are very, very clear. I mean, Nick mentioned some of them. I'm going to list some of them. The point is, yes, there is technology need to be progressed, and in order to enable them, but they are progressing much faster than quantum computing. Well, so please remember, quantum network advantage, quantum network supremacy, quantum network utility, whatever you say is done, proven, demonstrated. 50 years ago, we have Bell inequality, which is the exact demonstration of something you can do with quantum communication that cannot do with the classical communication. You want utility, QKD is a utility. You can make money out of QKD. So we are, in a sense, way ahead of quantum computing. And Nick was mentioning it. Why the whole focus is on quantum computing? Well, that's the investor appetite, that they want something crazy. Okay, so let me splash on you some of the things before I finally go to my talk, which is about verifiable cloud, to really emphasizing this large landscape of quantum network application, provable with advantage is there. One of the very, very breakthrough recently come from Alex in this group. It was saying, okay, let's assume in cryptography you want to reduce the assumption that you have. And that's very important. You know, all this assumption we make is become like a B-byte and billion wipeout. So if we can making sure that the assumption in our crypto system is continuously reducing, we're doing the right job, and quantum is doing the magic. If you take classical devices and you connect them with the old boring QKD, but this time as a quantum communication, this wonderful work is showing that Q-link plus one-way function, it gives you secure multi-party computing, something that did not exist. You cannot, in classical world, just use one-way function to achieve secure multi-party computation, but in the quantum world you can get. Well, here for you, quantum supremacy, deliver. And the protocol is being implemented in the lab next door with some of the people in the audience. Another thing, really, okay, when we talk about advantage, let's go to the network of satellite clock synchrony. I don't understand it, but it's actually a very concrete way of if you want to have better estimation of average phase shift that the physicist can tell you. This is very, very important because if the GPS is fall down and you want to make sure that you still have the right signal, well, you can do it with quantum communication and with the sharing of the entangled quantum state. And this is something you can implement, okay, maybe not with the satellite, although even Chinese have implemented with satellite, but this is the very, very simple work that you put entanglement and you take advantage, and is a proven advantage that you have with the network of the quantum clock as well as quantum sensor to get something that you could not do classically. So again, assume you have a bunch of sensors that is want to detect the whatever, I don't know, gravity of the length or whatever sensor you're putting in your devices, put the quantum communication, put the entanglement distribution around, not only you get a better estimation, but you also have a better protection about the noisy background. This is amazing. In fact, the quantum device give you enhanced and protection against the noise of the environment. These are all practical. These are all experimentally demonstrated. And they are company which actually making money out of the quantum sensing precisely within this construction. Even very nice other result, again led by Damien in our group, is that he has shown, now if you think about Internet of Things, when we talk about sensor, detector, privacy is again is issue. And what do the classical people do? They bring another gadget of FHE and SMPC and sit on top of all these things to give you IoT plus security. Well, guess what? Once you do with the quantum entanglement, not only get enhancement for free, you also get privacy because of the magic of quantum communication. So by design, you have privacy and authenticity. How do you do this? You need to have shared entanglement of the GH to the state, and you already have. This is yet another advantage that we know it exists. And the final pitch is like, which I think, although I pick up all of these things, I don't know how to link it to the blockchain, but I think these are very interesting. If you just think the use case, it becomes relevant. Another one is anonymous communication, which is, again, is a very funny quantum thing that, we have a network of people, too often wants to communicate, but they want to make sure nobody knows who are these things. Only Alice and Bob need to know that they are communicating. Impossible to do classically. Share them GH to the state, you can do it. And again, it's experimentally has been demonstrated that how could I do an anonymous transmission between Alice and Bob without anybody knowing that? Are you convinced there is enough advantage for quantum communication? Are you convinced that they are all demonstrated? So now I can go to the verifiable cloud the way I understand verifiable cloud and that I was pitching it. So this is what we believe in, this distributed network of putting quantum computer, classical computer. They might be connected using Q-line that doesn't need trusted node. They might be connected using QKD network that they need a trusted node, etc. They could be metropolitan. They could be not metropolitan. What I want to say is that this is going to be built. And in fact, already, for example, in Canada, they have demonstrated a quantum computer that they have with the photonic that is linked with the client that is photonic. So, and also IonQ has sold 2 machines to RNet, the security service that is, in fact, are connected using the entanglement. So we are already seeing bits and these pieces with the current quantum computer being implemented. There's many companies actually also working that is interconnected. So I don't think this is completely silly infrastructure. This infrastructure, we're seeing element of it. And now I want to pitch to you is like, what do we do? Why are we so excited if such a thing comes? Because again, we are able to do something with this thing that you could have not done classically, which was this verifiability, privacy by design, rather than put some overhead that comes and sit on top of it. Okay, you will hear about this talk from Beatrice, which is experimented, who actually implemented it. So this is a proof of concept of 2 servers which are untrusted. They could be noisy, they could be malicious, etc. And there is a client which is sitting in between, doing exactly what you were asking. The state comes, will pass, not be measured by the client. And what are they able to do? We are able to do proof of concept of this vision. Okay. There's lots of steps left to go there, but it's there. It's no longer science fiction. And I have one other argument, depending on how much time it is, but I want to say this is a very good moment. So thank you very much for Quantum Punk setting up this talk, because it's a very good moment to say we are at the moment that we need to tell to this network or a hardware designer a use case driven. This is my personal view, that infrastructure is not supposed to grow and to be implemented like what was the case in the classical, that they're building it up for the sake of build entanglement network, build, etc., etc. We can have a very concrete use case, exactly what you're saying. If we find the Zcash, if we find the application that makes sense, and then we can influence the design. And the story I want to tell you, if I manage to keep you all the way to the end, is that after 20 years of writing protocol, optimizing it, implementing it, and crashing it, etc., we have worked out a way that now we can go back to our hardware people saying that just give me this, which is called a box. You will see it in VeriQloud. We call it Charlie, but it in fact is a trusted, secure rotation. Just give me secure, trusted rotation, which is a single qubit rotation operation, and from there, I can build everything you want. And this is the moment that is very important to influence hardware, rather than waiting for them to do whatever they want and say, can I please plug my little rotator that I want to hear? But of course, this came because we had a vision and we have an idea and we have nothing else to do but write papers and try to optimize it. So here is really the case that maybe don't appreciate it, but it is our life story that we have now reached to the case of, you give me this, and I'm very modularly able to expand the number of servers, expand the number of clients, expand the number of maliciousness, and try to construct it. Every time, I'm just adding a tiny little thing on the same module. So remember the beginning of my talk, as I said, that this is a software hardware solution. So we have made our software to work with the same little hardware, which is the link. Okay. So a very history of the field. I should just do it, just to say that where everything comes from. So really, 20 years ago, this model of distributed quantum computing by Brigel Rossendorf was designed. Seilinger demonstrated the proof of concept of demonstration of this one-way computing. We have written a a language for it to make it abstract. And now all the photonic quantum computing that you see around the world, including the famous psi-quantum of raising billions, they are implementing exactly the same story. So this architecture that I'm going to define my protocol about, it is the architecture that is currently being built by Orca, by Quandela, by Quix, by Xanadu, by psi-quantum computing. They are not the gate-based model, they are measurement-based model, which is equivalent, but it's very important to emphasize that story is really rich to the becoming the architecture we have. A very parallel question, which is about this verifiability. It doesn't seem like it's about zero knowledge or verifiability, but it's exactly the same question. Scott Aronson, again, 20 years ago, asked a very simple question that, okay, let's imagine we have quantum computer. How do I know if it's really quantum computer? Because it's supposed to be beyond the classical simulatativity. Can I have verification? You know, it's not really zero knowledge verification, but in fact, you can make it a zero knowledge verification. It's interactive proof system. It's the same machinery that, can I have interactive proof system that my verifier is the BPP, is a classical computer, whereas my prover is the quantum one. And we thought it's such a simple thing that he offered $25. This is still an open question. And I believe it cannot be done using classical computer, but magically with quantum communication, we have shown that it can be done, and we have implemented. And there is a whole machinery of a completely novel method using multi-party scenario, interactive scenario, using entanglement, without entanglement, using coherent pulses. Like, there is a zoo of protocol that comes really addressing how do we do verification, which is the main toolkit we will use for semi of the talk. Then the multi-party computing started, the quantum internet. This is a very nice paper by Werner Group that are deciding, what are the stage of the various quantum internet, what kind of protocol we can do. And for me, one of my favorite recent breakthrough is the work of Christoph Schaffner, who's also probably going to talk about all this thing, but the multi-party computing. So we are not only trying to do classical multi-party computing, but we can do quantum multi-party computing. Somebody has the quantum data, somebody has a quantum machine learning fancy thing. Somebody built a quantum computer. They don't want to try to trust each other. They cannot trust each other. They cannot upload the data of a bank on a remote server somewhere, etc. So you need to have a QSMPC. And we are not able to have this QSMPC. And again, building block of connecting those nodes with the photonic, doing something, it's done. It's possible. Okay, the nodes are not very fully capable, but we are getting there. And this is the basis of the national infrastructure in Europe, in US, in China, in UK. We are all building this entanglement distribution infrastructure, which is enabling quantum SMPC. And these are important because you need the national government to build the bridges and the road so that we can infrastructure implement everything on top of that. And then I'm going to tell you exactly a lot of work that we have done within this domain to simplify it, to make it a practical solution that VeriQloud is trying to push in order to implement it. Okay. 23 minutes. I have 7 minutes left, according to slide. Okay, so let me, now we're going to do as academic talk. I'm going to stop pitching. I'm going to do a little exercise, okay? So let's try, it's not a proof, but it's closest that it gets. So let's take this example. This is the simplest example we can play around. And, these are 5 qubits, and they are entangled. So this is like an element that we have in all the lab. But once you think about a distributed computer, every one of them can be a quantum computer, or every one of them could be a classical computer. But this is a distributed language that I have the node. They are connected, usually WLink, interconnected, that can put them together. I don't care anymore about the structure of this. I'm just saying that this is a distributed architecture that is MBQC way of thinking about it. So if you were in the world that everybody's trusting everybody, I just pick up my phone and I talk to the cloud, please implement for me blah, blah, GHZ sensing algorithm, blah, blah, whatever thing that I was showing, everything that I was showing I want to implement. You would have just a classical client using some communication. Maybe they are post-quantum secure to make sure there is no eavesdropper in between. But you're essentially trusting the server, you're trusting yourself, you're communicating, you're implementing it. And now comes the question, well, obviously we are not in that world. If this transaction happened to be, I don't know, the signature of whatever big check on the blockchain that I want to exchange, I want to add a bit of the privacy and integrity on that. And what I want to show you, in order to add privacy integrity, you just need to change a little bit. So far, all the communication is classical, and you just add a bit of quantumness. So what is this? Before, I was talking only classically to all my to this server, to this provider that Nick was talking about that is sitting there. Now, I need to somehow insert my quantum key. You know, I need to put a quantum key. And this, in order to do quantum key, I don't need to have a trusted source in my home. I don't need to have a device measurement. I don't need to have quantum computer. I don't need to have a quantum memory. I don't need to have anything. So what do I need to have? I just need to have a wing ring. You know, remember the old wing ring that everybody, when they wanted to connect, they would bring the computer, they would plug. So we want something like this, that it's just a randomization. This device, the photon comes in. It could be microwave. It could be whatever way that the hardware is provided to it. It could be noisy. It could be malicious. I don't care. It just comes to my hardware secure module, which happened to be quantum hardware secure module. And this hardware secure module, you need to have the minimum thing. And that minimum thing is just a simple rotation. So thinking about this trusted single qubit rotation, you can call it quantum enclave. You can call it quantum trusted execution environment. You can call it my local, my local rotator. It could be through quantum link. It could be an infrastructure that I'm having a post-quantum secure access to it to do the rotation. In the only assumption that I need to do is that. And now, before I give all my classical communication to the server, which all those classical communication are one-time padded, the most secure way that you will talk over the channel, you are putting the key of your one-time pad using this. So something that you never do classically. If you do one-time padding, you never ever give your quantum, your classical key to anybody. In quantum world, you do. You one-time pad and you encode your key quantumly using this trusted execution environment, and voila, tamam shod. You're able to do everything from there. And you're able to do verifiability, privacy, and as I will show you, or Beatrice will show you, you can do multi-party. So that was just for privacy. And of course, you can ask tons of questions. What if I want to have only few of these things? Maybe I don't want to randomize every computation. Maybe I want to minimize the number of calls. Well, every time you need to look at it, there is optimization. There is tons of different ways that, depending on how much, let's say that you're doing machine learning and you want to hide some aspect of this data. You're not necessarily the whole data. Maybe you want to hide the bias of your data. Then you need to put only few calls to your execution environment. And maybe you don't need to also have fully blindness. Maybe you want to have verifiability. Again, you can reduce the number of calls, but that's the universal picture of it. And now, if you want to add verifiability, finally, I've finished with verifiability and we're done. What is verifiability? Verifiability, and I really want to know if this is the verifiability that you want, or is a different verifiability. We want to know that when I'm running this computation, when I'm running this preparation of the state, when I'm trying to sign my digital assets, I want to know that if it's really done correctly or not, okay? And what we do, the classic thing that you do, so you do exactly the same thing. We're not bringing a new hardware module, but you just do several shots. Some of them are your target computation, some of them are your test. So the only thing I'm not telling you exactly what is this colorful graph, what is the difference of this color graph with that, but this is exactly like it's a stretch to say this is proof of knowledge, but it's exactly the witness that we want to have, that if I, as a verifier, see the correct outcome coming out of this test round, then I can prove to you everything that you have done, all the other one is correct. This is the strongest notion of verifiability that as far as I know, can exist only in the quantum case. Because what do we say? We say that as long as this box could be tampered with, could be broken, it could be built by malicious party, I want to ask one property from it, that whatever noise, and here noise could be crypto noise, or could be hardware noise, it could be environment noise, as long as this noise doesn't leak the secret theta, that's the only parameter I want, then I can have for you the strongest notion of certifiability, that everything is correct, computation done correctly, implementation is done correctly. So that's, and yet remember, I'm using it only that box. This is what I wanted to show, that like we are at the moment that we can go to the experimentalist saying that build for me this box. I don't know, put a black box around it, do whatever it is, just make sure the theta is not leaked. Of course, there is many things you do. You use it post-quantum security, the remote state preparation, you can use quantum communication, you can use it quantum enclave. But once you give me this, the rest is just become the software which is optimized there. And then, of course, you can put on top of that, multi-party case. But let me just stop in here. So everything is done to building that box, that magical box, which, by the way, is the patented architecture of VeriQloud. Surprise, surprise. So how do we implement it? Tell me what is your network. If your network is the IonQ that is connecting internet, a bunch of ion trap using photonic links, that's where my box will sit here. This is exactly how I'm going to control to build a trusted network. If your network is the QKD type of network, like the one that Beatrice will show you, you have a bunch of sources that are noisy, you don't trust, somewhere quantum computer seeds, you're just able to send quantum link through them. Well, these are my bugs. I just put them and I can do it. If you have an enclave, we have built it, and this is a project that actually we are working with Thales with. If you give me your hardware secure module that I can throw through it a photon, well, I put my quantum hardware secure module on your center, and I classically talk with that hardware secure module to work on it. And even if you don't want to do any of these things and your continuum, but you have built you have built isolated gate zone. Isolated gate zone is the platform that they build in order to do fault tolerant. And they have built it in such a way that, like the sushi, when the qubit comes, they go in that corner in order to make sure they are not noisy. That's exactly what we use, and we implemented recently with them the largest ever MBQC blind verifiable computation on that case, which was a 53 qubit. And we simulated the trusted secure isolated single qubit using the trusted gate, even without quantum communication. So you see, let's talk more with the hardware people so they can build that building block. And I want to claim it's not anymore future secure fast network. It's something that is there, is right now. We can play with it, and depending on, it's maybe what we are lacking is exactly what hopefully the today is giving us. Tell us what should be that application, and we pick up all this massive toolkit that for decades we have built it, and we tune it and optimize it over there, because I think we have tried to optimize the assumption as much as possible. And I just want to mention, this is probably what Nico was saying, of course there is a completely different way of doing everything I was saying without using the trusted node that I was saying and using post-quantum secure network. And I think that's what you were saying, they are not practical, that the cost of one call to my box is equivalent to 1,000 qubits on the quantum server. Well, when the qubits are a lot, you don't need my box, and you go with the post-quantum. But right now, those boxes exist, so let's play with the box. And maybe in future, we will have a hybrid way of putting both post-quantum and classical, depending on distance and etc. Thank you very much for listening.
Hi, David from Project 11. You mentioned at the beginning that this would be good for energy savings. I'm just wondering, how much energy savings do you see, and do you think long-term that this could actually eat up all of the classical computation we're doing, or will there still be some use cases where we need to do the energy-heavy classical computation?
Thanks for calling me on that. So this is actually an energy initiative. If you want to have much more precise information, there is a quantum energy initiative run by a few of our colleagues that they are calculating very precisely what is the cost of quantum energy. Because indeed, many of us saying, oh yeah, quantum is also good for energy, but you need to go underline. So if you're building fault-tolerant quantum computing, the cost of that energy is also a nuclear power plant, depending on which platform you go. If you look at the PsiQuantum, what they're trying to build, but some people are pitching the room temperature, quantum computer, etc. So it's debatable that what will be the energy costs for quantum computing. But I think the calculation has shown, and it's going to be definitely less than OpenAI and GPU and blockchain, proof of whatever you guys are doing. So I think it needs to be a mix. So to go back to really precise the question, is not my expertise. I think we need to really see where is this hybrid. And you see that everybody's talking about AI and quantum and HPC coming together and trying to use the HPC, because even the current electricity bill that we have for, I don't know, a quantum computer of the IBM is way, way lower than what you would ever done for any HPC. So when people say that, oh, I've done something on quantum computing that can be simulated classically, but the cost of the energy is an advantage. And I believe same thing can be done for quantum communication. Once Mark convinced me, I forgot how, but essentially maybe there is something about the energy cost even on the communication, but I don't have the answer to that yet.
Cool, thanks. Thanks.
Hi, thank you very much for this excellent seminar. I just would like to comment a little bit. At the beginning, you said about the software, hardware integration for the quantum world, and you said that for the classical world, this is not possible. But it is done.
Yeah, it is done, and I'm
For
lying.
example,
I just, the story would be better.
Quantum cryptography, there is a strong integration on the co-design between software and hardware.
Correct,
And
correct.
there are many, for example, post-quantum cryptography design options for this co-integration between hardware and software. So
maybe I can clarify what I meant. You're right, the post-quantum, every algorithm we're doing is a co-design, but post-quantum is pure classical solution.
Yes, this I know, but you said it particularly for the software hardware co-integration. And this is also done in the classical world.
Yes, so
done. And it's done not only in PQC, but also with elliptical curve that are very heavy to run. So even before PQC, this is already done for certain sensitive applications.
okay, let me clarify. So I think it's a very good point. So maybe there is a misunderstanding for everybody. What I'm saying is that we do a lot of hardware, exactly as you say, hardware design, co-design, but the solution is using only classical mathematical tool. We agree on that.
Yes, but this
But
was
what
not
I'm
the
saying,
point
sorry,
that
let me say that. What I'm saying is that in quantum, we can use the quantum hardware. And actually, the thing that is done in classical, which is similar when you use hardware secure module. If you use trusted execution environment hardware secure module, you are coming, and this is the best way to bring security on top of AI, not doing it only with the FHE. You're also using enclave hardware. What I was trying to refer when I'm saying hardware software is use quantum key, quantum encryption as part of the hardware. Not in the case of adapt your software to the hardware that you have, but actually make as part of your solution a quantum element. But we can take it offline to discuss it more. But that's what I wanted to clarify.
Sure. Yes, because keys for encryption are also used for the hardware that we have now to boot them, really to at the very initiation of the hardware. So this is a very important point because it's really the root part of cybersecurity. And then you also said at a certain point anonymous communication that cannot be done classically. Also, but this is done.
Information theoretically secure. Thanks for quoting me that. So exactly, many of the things that we can do quantumly and cannot be done classically. When is the distinction is about information security versus post-quantum security. You're right. Thanks for the point.
And then, yes, I see something that I have to try to, let's say, how to say, integrate myself a bit with this concept, privacy equal integrity.
Yes.
Yeah.
What I meant is that...
they are not really equivalent, but so I have to absorb.
Okay, I'm happy that I confused you because in fact, it's the magic of quantum and the main message is that we only provide you privacy and that privacy is enable integrity. And that's something, again, is something that is very unique in quantum because I show you my box is just give you hiding, but because I have the hiding, when I'm running several shots, the device does not know, am I doing computation or test? So using privacy, I'm offering integrity. I'm able to give verifiability, which is utilizing the toolkit of the privacy. That's in that sense what I'm saying. The challenge of privacy is the same challenge of integrity. Whereas even in classical world, people have put YAO protocol, which is about the authentication plus with FHE to give you outsourced verification as well. In its same is the same thing, but here privacy enable integrity.
I understand. And this is what also Damien...
Sorry, so we are a bit late on schedule, so I would say
Sure.
let's take this offline.
Yeah.
Sorry.
Thank you. Thank you.
Thank you, Elham, again.